Hello again and welcome back. This is our first video lecture for Chapter 6 in our textbook. And the title of Chapter 6 is Force and Motion, Part 2. So we're really just continuing the ideas from Chapter 5, which I remind you was where we started what's called the study of dynamics, which explains why a particle moves the way it does, not just how. So we're going to continue with dynamics, and remember, the physics that we introduced in Chapter 5 in order to study dynamics was Newton's 3 laws of motion. The first law says that if the net force on a particle equals 0, then the velocity of the particle cannot change. The second law, in essence, tells you what happens when there is a net force on the particle. You get an acceleration. Net force causes acceleration. And the formula relating acceleration and net force is simple. Acceleration equals net force divided by mass. Although that's a vector equation and you must apply it by components. Newton's third law is a tool that's useful when you're applying Newton's second law. And Newton's third law is always talking about two particles. I often call them A and B. And Newton's third law says that if your particles A and B interact with each other, so that there are forces between them, then the force on A due to B and the force on B due to A have equal magnitude but opposite direction. And this is true no matter how big A is relative to B or how small A is relative to B. And we use those 3 laws in a lot of situations to study motion in Chapter 5. But you may recall, and I mentioned this in class, all of the surfaces upon which objects were moving in Chapter 5 were what were called smooth, or, better yet, frictionless, which is an idealization. You can get surfaces that are nearly frictionless in real life by using lots of lubricant of one kind or another. But in normal everyday life, surfaces are what you might call rough. And there are what we call frictional forces that act between surfaces in contact. And that's what we want to understand in this first part of Chapter 6. Okay? So the reading that goes along with this video lecture is Chapter 6, Section 1, Friction. I strongly recommend you take the time to read in Wiley Plus this section, Chapter 6, Section 1. Because there's a lot more information about friction than what I'm going to supply to you in this video lecture. Remember, my video lecture is a summary of the key ideas in the reading, not a complete repeat of everything in the reading. But one of the things that you will learn about if you do the reading in Chapter 6, Section 1 is where do frictional forces between two surfaces in contact come from? How do they arise? And to be perfectly honest with you, we don't completely understand frictional forces. They're still an area of study. That's called tribology, the study of frictional forces. Physicists and engineers, there are those who study tribology, frictional forces. But the basic idea is this. If you have two surfaces in contact, a surface and then an object sitting on top of the surface, right? That's two surfaces in contact. Even if to the naked eye those surfaces look smooth, if you zoom in and look more on the atomic scale, they're not smooth. They're bumpy. There are always going to be some bumps and irregularities. And in some cases where these surfaces are in contact, you'll have a downward bump from the upper object coming into contact with an upward bump from the lower object. Okay? And where those bumps come together, the atom of the top object and the atoms of the top object and the atoms of the bottom object have an opportunity to bond with each other in those regions where those bumps are in contact. And what the engineers call those are cold welds. So welding without heat. It's just atoms bonding between the two surfaces. And that's the ultimate cause of frictional forces. Atomic interactions, bonds between atoms of the two surfaces. Well, as you might expect, that can get very complicated to study. So what we're going to supply are empirical big ideas, results from experiments that do a decent enough job explaining how frictional forces behave. Good enough for what we're going to do. Okay, so let me start then by summarizing some of the key ideas, the key properties of frictional forces. And I'm going to start that by cutting over to Wiley Plus. Pardon me for a moment while I move my mouse around. Sorry, I have to. I'm having a hard time getting my mouse to go where I want it. Let me try it this way. Okay, there we go. Sorry for the delay. And now what I'm going to do is I'm going to run an animation that's going to show you some of the behaviors of frictional forces that we need to understand. We start out with a block sitting on a horizontal surface, but it's rough surface. There's going to be frictional forces if needed. And right now, there are just two forces. The force due to gravity vertically down, and what we call the normal force, perpendicular to the surface on the block, in this case acting vertically up. And there are no other forces, no other pushes or pulls on the block. So the downward force and the upward force, F grav and F normal, balance. And that's it. That's the end of the story. But now, in just a moment here in the animation, we're going to apply a horizontal force to the left. We're just going to call it an applied force, F. There it is, F. But let's observe, the contention is that the block doesn't move, right? I'm pulling to the left, but not terribly hard. And my observation is the block still remains at rest. You can imagine that. You can imagine an object on a surface and you pull on it a little bit, but it doesn't move. So there must be a force to the right balancing the applied force F. And that force comes from the bonds between those atoms, between the block and the tabletop there. And that force from those bonds between the surfaces is parallel to the surfaces and is called a frictional force. And because the block isn't moving here, we call it a static frictional force. And so that's the block labeled, the arrow, labeled F sub s, little f sub s, pointing to the right. Static frictional force. And it will be exactly the same magnitude as the applied force to the left, as long as the block doesn't move. Okay? And that means then that static frictional force is rather tricky. Because what if I come along with this applied force and I pull a little bit harder to the left, okay? Now that applied force is bigger, but still not so big that the block moves. Understand what I'm saying? Still, the block is stationary. So that must mean that the static frictional force got bigger the other way to match the applied force. Has to. If the block is staying at rest, its horizontal acceleration is 0, so its horizontal force, net force, must equal 0. So if the applied force is to the left, there must be a force to the right that balances it, and it's static friction. So the static frictional force got bigger there, just to balance the applied force. Well, what if we make the applied force bigger still? Well, static frictional force got bigger as well, the other way. So the static frictional force is going to be as big as it needs to be to keep the block from moving. Now, everybody knows in a situation like this that if you make the applied force to the left large enough, if you pull to the left hard enough, you can get the block to slip to the left. And now the animation is showing that with a larger applied force to the left and this shading behind the block over here on the right side to indicate motion. So what that is saying is that if you pull hard enough to the left, you can break the bonds, the cold welds between the block and the tabletop, and you can get the block to slip. Of course you can, right? If you pull hard enough. So there must be a maximum value to F static friction, which we're going to talk about. But now it's sliding to the left. It's going to show this now happening. Okay, now we have motion to the left. We say the block is slipping. Let me pause the animation. The block is slipping to the left, and now those cold welds between the block and the tabletop aren't nearly as strong, and you still have a frictional force, but it's not as strong, and it's given a new name. It's called kinetic friction. Kinetic is a word for motion, because we have motion between the surface of the block and the surface of the tabletop. So now the frictional force to the right, opposite to the direction of the sliding, is labeled F kinetic. And now, of course, notice you have a net force to the left, and the block's going to accelerate to the left. It's going to speed up. But what if I pull a little bit less hard with my applied force, like that showed? Now my applied force exactly matches that kinetic frictional force. Now it will just travel to the left at constant velocity. It won't speed up anymore. So there was quite a bit going on there, but it encapsulates the key points about frictional forces. There are basically two kinds. There's a static frictional force. That is what you use if the block and the tabletop aren't moving relative to each other. And a kinetic frictional force if there is slipping between them. Now this shows a graph of the magnitude of the frictional force versus time, where we started out with no applied force, and then we had the applied force F to the left, and initially the block did not slip, so the static frictional force just balanced the applied force, so the static frictional force just keeps getting bigger and bigger until you get to what's called the breakaway point, where static friction reaches its maximum value, Fs max. And that's what this shows. And then you have slipping. The block will slip to the left. The kind of friction now becomes F kinetic. It's now much weaker, and you just have a more or less constant, weaker frictional force called F kinetic. Okay, so that animation it tells us kind of the key ideas about the behavior of the frictional force. So I want to summarize those in these bullet points that I have on the slide now. Okay, if there is no slipping, so now again I'm imagining a scenario where I've got a surface and I've got an object in contact with that surface, like a block on a tabletop. Two surfaces in contact, okay? If there is no slipping between the two surfaces, they are at rest relative to each other, then we would have a static frictional force, little f sub s. And its whole purpose is to attempt to prevent relative motion between the two surfaces in contact. So the way that happened in our animation is if I have an applied force, capital F, say in one direction, and there's no slipping between the block and the surface, then there is a static frictional force that exactly balances that applied force to keep the two surfaces from slipping relative to each other. Okay? However, the magnitude of the static frictional force has a limit to it. It can only get so big. There's an upper limit, a maximum value for two given surfaces. And that's important, because that's, of course, how you get things to slip. You have to give an applied force that exceeds this maximum F static. And it turns out, by experiment, you can come up with the formula for the magnitude of this maximum F static. So now I want you to look at this picture here of the block on the tabletop. And I'm going to change the way I label this just a little bit. I'm going to take an applied force that's pretty big, okay? And I'm going to draw in the static frictional force in a second. This applied force is so big, what I'm imagining right here, that if I pull even the tiniest bit harder to the left, the block's going to slip relative to the table. So when I'm in that situation, where my applied force is so big that if it's just the tiniest bit bigger, the block's going to slip, we say that the block is on the verge of slipping. That's an important phrase when you have a frictional force, okay? We say it's on the verge of slipping. word there is slipping. Okay, I moved myself. It's on the verge of slipping, okay? If that's the case, then the static frictional force that's opposing the applied force is exactly the same magnitude as the applied force because there's still no actual slipping, but it is the maximum of F static. So it would be labeled Fs max. And as I'm telling you, there's a formula for the magnitude of Fs max for two surfaces in contact. And it's right there. And that is really important formula when you're talking about friction. The formula for the magnitude of the maximum static frictional force, Fs max. It depends on two things. How big is the normal force between the surfaces? And then there's this other constant mu sub s called the coefficient of static friction between the two surfaces. So if I go back to my free body diagram and finish it out, because it isn't complete, there's of course a gravitational force or force due to gravity straight down and a perpendicular force from the surface straight up in this case, and we would call that the normal force, F normal. And what we're telling you is that the magnitude of Fs max depends upon the magnitude of F normal. And remember, the normal force is a reaction to the two surfaces being, pressed together. So the harder the surfaces are pressed together, the larger the normal force. The larger the magnitude of the normal force, the larger the magnitude of Fs max. Okay? All right, I want to show you that now. I'll try to get back over here if I can. Yep. With another animation. Get that. Okay, and now I want to show you this animation. And it shows a block on a tabletop. And the block has a mass right now of 1 kilogram, and it's got shows forces, F grav down and F normal up. And we're going to apply the force up here with the slider. There's an applied force in newtons. And it will be, here we go, it will be to the right. It's the arrow pointing to the right. But the block's not slipping, so that arrow that you see to the left must be F static. And if I keep applying with a bigger force, of course, the applied force and the static frictional force get bigger. And it turns out the animation tells me when I've got the block on the verge of slipping. In this case, I need an applied force of 5.928 newtons. Okay. Then we are on the verge of slipping. That means that the F static that we see here is Fs max. Now, what is the magnitude of the normal force in this case? Well, there's just F normal up and F grav down. Those are the only vertical forces. There is no vertical motion, so the net vertical force must equal 0. So the magnitude of F normal must equal the magnitude of F grav. So in this simple case, the magnitude of F normal equals mg. M is 1 kilogram, g is 9.8 newtons per kilogram, mg is 9.8 newtons. Right? You need to be able to think all that through. So the magnitude of the normal force on the block is 9.8 newtons. And Fs max is proportional to that F normal of 9.8 newtons. Proportional. Not equal. Proportional. Now what I'm going to do is take away the applied force and double the mass that's sitting there. It's now 2 kilograms total. You can see F grav got longer down and F normal got longer up to balance. And now let me apply the force to the right again. And I keep making the applied force bigger, and F static keeps getting bigger and bigger and bigger and bigger and bigger and bigger. And now I have to go all the way up to 11.968 newtons to get ourselves to the verge of slipping. And now that Fs max to the left is quite large. In fact, what's F normal in this case? It's doubled, right? It's now 2 times 9.8, or 19.6 newtons. So I doubled the magnitude of the normal force. And what happened to the applied force for slipping? 11.968. Before it was 5.98. It doubled too. In other words, Fs max magnitude doubled when F normal magnitude doubled. Now let's take away the applied force, and now let's triple the mass of the blocks compared to the initial value. And applied force, bigger, 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 bigger. Now we're on the verge of slipping, okay? And now we have to go up to 17.67 newtons. Actually 17.95, I haven't pulled it all the way over. That's triple what what Fs max was at the beginning. But F normal has tripled too. So the whole point is just to show you that the magnitude of Fs max is proportional to the magnitude of F normal. Double F normal, you'll double the magnitude of Fs max. Triple F normal, you'll triple the magnitude of Fs max. Okay? All right. Now, back to our slides. So that constant that you see there between Fs max and F normal is the Greek letter mu with a subscript s. Mu sub s, you could say. And it's a dimensionless constant called the coefficient of static friction for the two surfaces. It depends entirely on just what are the two surfaces. What are they made of? That's it. Okay? All right. So everything we need to know about the static frictional force is more or less encapsulated in two ideas. That the magnitude of F static will be less than or equal to the magnitude of F static max. F static can never exceed Fs max, and it will be whatever it needs to be less than Fs max to satisfy Newton's second law. And there's a nice simple formula for the magnitude of Fs max right there, and we need to be able to use. Okay, so that's the situation with static friction. Now, as we showed in the animation at the very beginning, if your applied force in a particular direction is large enough, of course you can get the block to slide across the table, or you can get the two surfaces to slide relative to each other. And when there's relative motion between the surfaces, there's still frictional force, doesn't disappear, but it changes slightly, it's weaker, and it's called the kinetic frictional force, little f sub k. So that's the frictional force that acts on each surface when two surfaces slip relative to each other. And I'm going to tell you the formula for that magnitude of F kinetic, because there's just an empirical formula for it that we're going to use. And warning, it's rather similar to the formula for Fs max, but its own distinct formula. It says, the magnitude of the kinetic frictional force is equal to a dimensionless constant called the coefficient of kinetic friction, mu sub k, times the magnitude of the normal force. And that applies when there is relative slipping of the surfaces. And as I said, mu sub k is a dimensionless constant called the coefficient of kinetic friction for the two surfaces. So that's the formula we'll use to calculate the magnitude of the frictional force when the surfaces slide relative to each other. And some of the things we'll have to practice with is figuring out, if it's not told to us in the problem, whether two surfaces are slipping relative to each other or not. Turns out we have all the physics we need on this slide to do that, but it takes practice to see how you do it. Let me just also show you, just for your edification, some values of coefficients of friction for different two materials, right? It's always talking about two materials in contact. There's one column that has coefficient of static friction, mu sub s, and another column that has coefficient of kinetic friction, mu sub k. No units, because both of these coefficients are dimensionless. Then in the first column, you just have a whole bunch of listings of one material on another. Like the first one is steel on steel, then aluminum on steel, then copper on steel, then rubber on concrete. Think about what that might apply to. Automobiles, wood on wood, glass on glass, waxed wood on wet snow. Skiing, metal on metal with lubrication, like in a combustion engine. ice on ice, Teflon on Teflon, the cooking surface, Teflon, between the synovial joints in humans, in your joints. Now, basically, the larger the coefficient of friction, the more the surfaces want to bond with each other, the larger the frictional forces you get, the stickier they are. Okay? Okay, now, so you can look here and you can see, you know, like rubber on concrete, the coefficient of static friction is 1. The coefficient of kinetic friction is a little bit less at 0.8. 1 is considered pretty good size. But there's nothing that says you couldn't have two surfaces for which the coefficient of static friction was larger than 1. And very small values compared to 1 for a coefficient of friction means the surfaces really don't stick much, like between the joints in humans, or when you have Teflon on Teflon. So a lot of times in the homework problems, we'll be given outright one or both of the coefficients of friction for the surfaces, and we'll need to use those then in solving the problem. Although occasionally the problem will give us other information and we'll have to end up solving for the coefficient of friction. But I want you to see some values of coefficients of friction. Now we're going to start practicing, and then we'll be doing more of this in class. Okay, now, here's a scenario we're just going to work our way through briefly, and then I'm going to leave you with a class engagement exercise to do on Blackboard. So, here we go. Suppose I place a block on a horizontal floor, regular floor in a room, so you know that there's friction if you need it. But I don't push or pull on it. Is there a frictional force acting on the block? I'd like you to pause the video and think about that and get your own answer in your head. You can pause, obviously, you can take as much time as you need and then come back. So what I would recommend you do, I hope you did this, is to help you visualize, make yourself a sketch. There's the horizontal floor. Okay? There's the block. But I'm not pushing or pulling on it. So the implication is there's nothing pushing or pulling sideways, but if I want to draw the free body diagram, which I ought to be able to do, of course, Earth pulls down, gravitational force, and the block is in contact with the floor as surface, and so there's a reaction force that's perpendicular to the surface, called the normal force, but nothing's moving, right? Block's not moving. So I know these two forces here balance each other, and that's the whole story. That's the complete free body diagram. There are no other forces. So there is no F static in that case, right? There could be a situation, even if the floors are rough, where you don't need a frictional force. Okay? Frictional force, like the normal force, is an example of what's called a reactionary force. It reacts to the situation. That's why there's no canned formula that you can always use for it. Let's keep practicing. Let's go on to B. Now I'm going to apply a horizontal force of 5 newtons to the block, but the block does not move. What is the magnitude of the frictional force on it? Pause the video, think about it, and then come back. Okay, now we're answering part B. So now, let's say my applied force is to the right. I'll just call it F. That's my horizontal force of magnitude 5 newtons. But the block does not move. That means its acceleration is 0. That means the net force on it must be 0. So something has to balance that applied force to the right. And of course it has to be very specific, static frictional force, little f sub s. And now the magnitude of F sub s is not 0, but it exactly balances the magnitude of the applied force, so it's 5 newtons. Okay? Nothing more to it than that. Now let's go on to C. Let me tell you now that the maximum value, Fs max, of the static frictional force between the block and the floor is 10 newtons. I'm just telling you that fact. Here comes the question. Will the block move if the magnitude of my horizontally applied force is 8 newtons? Pause, think, and come back. Okay. Welcome back. Now, they're telling me in this problem that the magnitude of Fs max between this block and this floor is 10 newtons. That's the biggest F static I can possibly get if I need it. All right. My applied force now, right here, has a magnitude of 8 newtons. If F static can balance it, then that's what's going to happen and there'll be no motion of the block. So the question is, can F static balance that applied force of 8 newtons? Sure, that's why I needed to know what the Fs max magnitude was, because I can't get an Fs bigger than Fs max. But all I need in this case is an Fs magnitude of 8 newtons to keep the block from moving. That's less than the maximum for Fs, Fs max is 10 newtons, no problem. The surfaces can provide me the F static of 8 newtons that I need to keep the block from slipping. Okay? So that's actually the answer to C and D, because D says in this case, what is the magnitude of the frictional force? There's no slipping. So in this case, the frictional force balances the applied force, 8 newtons. Now let's go on to E. Will the block move if the magnitude of my horizontally applied force is 12 newtons? Okay? The magnitude of my horizontally applied force is 12 newtons. Okay? Pause the video and think about it. Okay, well, if my applied force is a magnitude of 12 newtons, to keep the block at rest, I would need an F static of 12 newtons. But the most I can get, Fs max, is 10 newtons. So if you need an F static more than Fs max, you can't get it. If you can't get an F static of 12 newtons, there's no doubt the applied force is going to be bigger than the frictional force, and the block is going to slip, in this case, to the right. Okay? All right, now, the next practice I'm going to let you do, as I said, as a class engagement exercise. I'll create the assignment on Blackboard as usual, and you will enter your answers there. Okay? All right, let me explain the situation. We know in physics, physicists love to put problems on inclined planes, as I've mentioned before, because as I've also said before, putting a problem on an inclined plane literally makes you look at a problem from a different angle, and that can be useful. So here's the scenario. This figure shows an applied force. It's applied to a block. The block is on a ramp, and there is friction between the block and the ramp. And axes have been chosen for me, x and y, where x is parallel to the surface and y is perpendicular. Note then, this applied force F, like you can imagine it's coming from you or me, pushing, we've got the block on the inclined surface and we're pushing kind of down and to the right. Okay? And that's the applied force, right there, shown. And apparently it makes an angle phi relative to the inclined surface. That's what the picture shows me. Okay? The incline itself, so phi is the angle that my applied force makes with the surface of the incline. Now, independent of that, there's the angle theta, which is just the angle of the incline relative to the horizontal. The block, I am told, does not move. That's important. It is stationary. So that's the scenario. Note, by the way, that this drawing is not a complete free body diagram for the block, right? A complete free body diagram would show all forces acting on the block. This only shows one force acting on the block. So if you want some really good practice, although I'm not asking you to do this for the class engagement exercise, draw the complete free body diagram. Okay? It can be a little bit subtle, but it's good practice. Here are the questions, though, that I'm going to have you answer. They're labeled here, A, B, and C. A says this: what is the component of the applied force that is perpendicular to the ramp? Not parallel to the ramp, but perpendicular. That's one of those axes directions, yes? It's either X or Y. That's perpendicular. Choose from among the following options: positive magnitude F sine phi, positive magnitude F cosine phi, negative magnitude F cosine phi, negative magnitude F sine phi. In essence, you need to be able to draw the component triangle for that applied F. And tell me which one of the components is the component that is perpendicular to the ramp. Okay, that's A. B, when you apply this force F, what happened to the magnitude of the normal force on the block compared to when you didn't apply this force F? So when you do apply this force F in the direction shown, what happens to the magnitude of the normal force on the block? Does it increase, decrease, or remain the same? Okay? When I apply my applied force F down and to the right on the block, what happens to the magnitude of the normal force on the block? Does it increase, decrease, or remain the same? That's B. And then C. When that applied force was applied, F, what happened to the value of Fs max, the magnitude of Fs max? Did it increase, decrease, or remain the same? Okay? When that applied force was applied, what happened to the magnitude of Fs max? Did it increase, decrease, or remain the same? So I want you to answer these as class engagement on Blackboard. Okay? All right, so that's laying the groundwork for applying, for studying frictional forces, and we'll be talking then, practicing more about that in class. But for now, that's all for this video.